For over a century, electricity has been controlled by physical, moving parts, electromechanical switches. That is now changing. We're shifting to a system based entirely on semiconductors. This is the transition to solid-state power.
Our analysis will cover 5 sections. We'll start by defining what solid-state means. Then, we will compare legacy and solid-state circuit breakers, followed by a similar analysis of transformers. From there, we'll examine the system-level implications of this technology. We'll conclude with the current adoption pathways and the key challenges that remain.
So let's begin with the core principle driving this shift.
At its core, solid-state power replaces mechanical components with semiconductors. Instead of a physical contact opening and closing, a device like a transistor controls the flow of electricity electronically. Because there are no moving parts, 2 major failure modes of mechanical systems are eliminated: physical wear and tear and electrical arcing. The prevention of arcing is a critical improvement for both safety and reliability.
Now, let's look at a direct application of this principle in electrical protection by comparing the traditional circuit breaker to its solid-state counterpart.
A mechanical breaker works by physically separating metal contacts to stop the current. A solid-state breaker uses semiconductors to halt the flow of electrons electronically. It is a purely electronic switch with no physical motion.
The primary difference is speed. When a mechanical breaker opens under load, its response time is measured in milliseconds, during which a destructive electrical arc forms. A solid-state breaker operates in microseconds, 1,000 times faster. This speed is sufficient to interrupt the current before an arc has time to ignite, preventing the associated damage.
This table quantifies the advantages. The response time improves by orders of magnitude. Physical wear from arcing and contact erosion, a primary failure mode in mechanical systems, is effectively zero. This means reliability is consistently high and does not degrade with use. And finally, mechanical breakers are passive devices. Solid-state breakers are intelligent, containing embedded microcontrollers that make them programmable. This is not just theoretical. Companies are actively commercializing this technology. For instance, Ideal Power has developed its B-TRAN bidirectional switch, and Atom Power is deploying patented solid-state digital circuit breakers in industrial and commercial settings.
So, beyond protection, these same solid-state principles are fundamentally changing power conversion, specifically the transformer.
A solid-state transformer, or SST, is not a direct one-to-one replacement. It's a multifunctional power electronic converter. It uses high-frequency switching and digital controls to perform voltage conversion along with many other grid support functions. A conventional transformer relies on a large iron core and operates at the low grid frequency of 50 or 60 Hz. Its size and weight are dictated by these physics. An SST operates at much higher frequencies, in the kilohertz range. Because the size of magnetic component shrinks as frequency increases, an SST can be dramatically smaller and lighter for the same power rate. The true capability of the SST lies in its integrated functions. In addition to voltage conversion, it provides inherent flexibility for AC to DC and DC to AC power flows. It can regulate voltage and correct power factor in real time. It naturally supports bidirectional power flow, which is crucial for integrating renewables and energy storage. And it comes with built-in communications. It effectively consolidates the roles of multiple pieces of grid hardware into a single software-defined device. When you combine these solid-state components, the breakers and the transformers, you're not just improving parts, you're creating a new type of infrastructure. This is the central thesis. Solid-state power is an infrastructure shift. We are moving from a system of discrete, passive mechanical components to a unified programmable layer where the flow of power is controlled by software. This new programmable layer has specific capabilities. Its high-speed control enables seamless integration of intermittent renewables. Its high power density allows for the efficient design of large-scale EV charging hubs. For data centers, its microsecond-level fault response provides a new tier of reliability, and its intelligence is the foundation for managing complex, decentralized, smart microgrids. Given these capabilities, we will now examine the practical realities of adoption and the technical hurdles that remain.
Adoption is occurring in phases, led by sectors with the most acute needs. Data centers are first, because the cost of power failure is extremely high. Defense and critical industrial applications follow, driven by the absolute need for reliability. Next is EV infrastructure, which requires high power density. Grid-scale adoption by utilities will be the final phase, reflecting the high capital costs and conservative pace of infrastructure modernization.
Three key challenges are still being addressed. The first is cost. Solid-state systems are not yet cost competitive with mature, mass-produced legacy equipment. The second is thermal management. The high power density generates significant waste heat that must be dissipated to ensure component lifetime and reliability. And the third is standardization. New protocols are needed to ensure these digital assets can integrate safely and reliably with the existing analog grid.
This brings us to the ultimate implication. Control over electricity is fundamentally moving from the physical domain to the software domain. The physical constraints that shaped our current grid architecture are being removed. The question is no longer just how to build better components, but what new grid architectures are now possible when power itself is programmable.